All right. Small angle. So we're going to tell you about the small angle approximation and then the simple pendulum. The small angle approximation states two important things: is that the sine of theta for small angles is approximately equal to theta. It also tells us that cosine of theta is equal to 1 minus theta squared over 2. Okay. Now, the proofs of those approximations is based upon a it's like a proof involving a triangle, and it has kind of like it has a weird like kind of arced leg. That's a geometric proof for it. There's a bunch of other proofs. I think there's a calculus one that involves L'Hopital's rule, but that's all kind of outside the scope of this. You really don't need to know how we got it. You just need to know what it is. But again, like I said, we got it from like a triangle that has a really small angle, and the leg is not like a straight leg. It's actually kind of like arced. Okay, but yeah. So what I'm going to do first is I want to show that the simple pendulum is simple harmonic motion, meaning I need to prove one of those points from section 1. Well, I actually can prove it with just two statements, but I do need to show and actually use the simple harmonic, or um, the small angle approximation. Okay. Well, first off, okay, I know that um, if I'm trying to get, obviously, I've, I'm going to draw this all the way down. I've traversed a length here. That's an arc length, okay, because it's a kind of a circular segment of, it's a round kind of segment, okay. So I know that this is going to be S equals R theta is one thing I can do, okay. Now, what I'm going to do, okay, is I'm going to differentiate this twice, and I'll tell you why I'm going to do that here in just a minute. I'm going to show you or there's a reason I'm doing this, okay? So this is going to be ds dt equals r d theta over dt, and then you get d squared s over dt squared equals r d squared theta over dt squared. Okay, so I just differentiated it twice, and I'll show you why I'm doing that here in a minute. Now, it's going to seem like I'm kind of changing gears real quick, but I want to start in this with F net equals MA. Okay? F net equals MA. All right? Now that I've started with this, okay, I actually need to figure out what my net force is. Well, notice that the tension force is pulling up this way. That's actually going to cancel out the mg cosine theta, because ideally the ball is not moving in this direction at all. Instead, it's moving, in kind of a swinging motion. What's causing that motion is actually the mg sine theta term. Okay? So I can actually do mg sine theta. I'm going to make this negative because it's actually opposing my motion, equals ma. Okay, and now I recognize that my m's can cancel out. Okay, so I've got negative g sine theta equals ma. Okay, now take a look over here. I wrote this expression, okay, and I said d squared s, the second derivative of s, which s is position, okay, or kind of like the length that I've traversed. The second derivative, or acceleration in this case, is equal to r second derivative of theta. Okay, so what I can do is I can actually make the substitution. Acceleration is equal to r second derivative of theta. So that's exactly what I'm going to do. I'm going to do negative. Oh, and I'm so sorry. Let me make a quick replacement here too. R is actually just going to be L. Okay, so I'm actually going to replace R for L when I substitute it in here. So I get G sine theta equals L d squared theta over dt squared. Okay? Now, there's one more thing I need to do. If I divide by L on both sides, you're going to see something kind of familiar happen. Okay? And I end up getting d squared theta over dt squared equals negative g over L sine theta. Huh. Does that look familiar? Or what? Oh, wait, it doesn't look familiar yet. You know why? Because there's a small angle approximation. This says that it says for small amplitudes, which means small angles, I need to approximate sine theta as being theta. Okay? So when I rewrite this, this hopefully should look familiar now to you. Okay? So negative g over L theta. Does that look familiar to you? I hope it does, because that right there is the simple harmonic motion differential equation. Okay, I've been saying it a lot this unit, but that's really what it is. We use it so often here. Okay, the simple harmonic motion differential, in case you forgot, right, was d squared x over dt squared equals negative omega squared times x, right? Well, guess what? I've got all my analogies here. Second derivative of a position or angle, I guess. This is what negative omega squared is. And then this right here is my position or angle or whatever, right? And remember, this differential equation serves no purpose to us other than to tell us what omega is. So I've got that negative. I'm actually going to just, well, no. Well, we guess negative omega squared is equal to negative g over L. If I drop the negatives on both sides and root, I end up getting that omega should be equal to root g over L. Okay? I also know that omega is equal to 2 pi over period t. Okay? Well, this is the same thing as saying root g over root L. So I can actually just, what I ultimately need to do is I want to flip both sides of this so I can get t on top. So when I do that, I get t over 2 pi equals, equals root L over G, okay? And then multiply by 2 pi, and you get the period equation that we all know and love, which is 2 pi root L over G, okay? So I just proved simple harmonic motion, right? We've shown that it fits the simple harmonic motion differential equation, which means it's simple harmonic motion. We've shown that that's how you get the period using small angle amplitude, or using small angle approximation, okay? Okay. I don't think I'm missing anything for that part. Let's see. The next part here is about a pendulum, and the problem text is kind of funny, but it says that simple pendulum, write an equation for the height and potential energy of a simple pendulum's bob as a function of theta. Okay. Notice that I'm looking for this lowercase h right here. Okay. Well, you might say, well, lowercase h is the height difference here is just L. No, it's not L. You actually have to use L, but it's not going to be. Well, I want you to recognize this, okay? This part that I'm going to shade here in the red, okay, is going to be a part of that right triangle that this makes, okay? This part right here is adjacent to the theta, okay? So this is going to be L cosine theta. Okay. When I add on this little piece down here, well, this whole height right here is going to be if the pendulum's at the very bottom. That's just, the whole thing is just L. So to find what I really want to find is I want to find just this little piece right here. Okay. This little part right here. Well, I can just take the whole length L and subtract it from L cosine theta. Why didn't I just do that? Okay, that's the easiest path forward from here. So I'm going to say that height has to be equal to L minus L cosine theta. That is technically an expression as a function of theta. Really quickly too, I can pull out my L's here, and it ends up being L times 1 minus cosine theta. Okay, I actually like the simpler form a little bit better, so I'm going to stick with that one. To get the potential energy, okay, to get the potential energy, right? The potential energy is just going to be mgh. Now, remember, if you remember, I think last section I said that mgh doesn't even matter in a spring mass oscillator. Yeah, but this isn't a spring mass oscillator. This is a simple pendulum. Okay, so mgh still counts here. Okay, well, h is actually L times 1 minus cosine theta. So this is actually just mg L 1 minus cosine theta. And the one other thing that you forgot, maybe you forgot this, is that the small angle approximation says that cosine theta should be equal to 1 minus theta squared over 2. Okay? So this really is just becoming mgl 1 minus 1 minus theta squared over 2. Okay? And what you hopefully should recognize is that this is 1 minus 1, so kind of just goes away. Okay? So these two are going to get neutralized. Okay? And you end up with, this is just going to be mgl times negative theta squared over 2. So you should end up getting that the potential energy is going to be equal to about negative 1/2 mgl theta squared. Okay. Yeah. I mean, that's kind of a weird looking equation, but it is what it is, right? Can't really do much about it. Okay. All right. I think that's it. I did get an expression for that in terms of the. I mean, I guess technically it was there too, but yeah. Okay. Yeah. Sounds good. Okay. All right. Well, there's that. Okay. Have fun. Bye.